Okay, today we will try to analyze single phase induction motors as a particular case of an asymmetry of a polyphase induction machine. As discussed in the last lecture, we will try to use the concept of symmetrical components and get the performance equations or equivalent circuit for the single phase motor. Okay. So, what we do is we take a symmetrical polyphase machine, okay, and see how it behaves under asymmetrical conditions, right. So, that is the purpose of today's lecture. Okay. And we have already discussed about the concept of symmetrical component, okay, which is basically to make asymmetrical systems or unbalanced systems as positive, negative and zero sequence systems. And we also said that positive sequence system will be analogous or related to forward rotating field, and negative sequence system will be analogous or related to the backward rotating field. Okay. So, this is okay, right. Now, we have, supposing if it is a star connected 3 phase induction motor, and if you apply a positive sequence voltage, okay. So, the voltages, if you apply VL here, supposing these are the terminals ABC, so you apply VL here, okay, and maybe A square VL here and A VL here, is not it, because you apply a 3 phase voltages. So, VL will be across AB and A square VL here across BC and A VL here across AC or CA. Okay. And you know the currents IA will be I naught plus I 1 plus I 2 and IB will be I naught plus A square I 1 and IC is this you are aware. What will be the 3 currents using symmetrical components. So, the individual currents you can get it from the symmetrical components, and VA will be V naught, V 1, V 2, is not it. What is V naught is I naught Z naught, V 1 is I 1 Z 1 and V 2 is I 2 Z 2, right. These are the sequence, because we have 3 impedances Z 1, Z 2, Z naught, Z 1 positive sequence impedance, Z 2 negative sequence impedance, Z naught is the 0 sequence impedance. Okay. So, what we are trying to say is that positive sequence you have V 1, Z 1, I 1, okay. So, that V 1 is Z 1 I 1. Negative sequence we have V 2, Z 2 I 2, so that V 2 is Z 2 I 2, and we have 0 sequence we have V naught, Z naught I naught, so that V naught is Z naught I naught. Okay. So, we consider a 3 phase machine. So, all you need to know is what is Z 1, Z 2, Z naught at a given speed, then knowing V 1, V 2, V naught you can find out I 1, I 2, I naught, and so you can find out you have VA, VB, VC, and V naught will be same for all the 3, but the positive sequence will be V 1 A square V 1 and A V 1, and here V 2 A V 2 and A square V 2. Okay. So, these are the equations. and for the case of a star connected machine, the sum of the 3 currents will be 0. IA plus IB plus IC is 0 because star connected and neutral is open. Okay. So, therefore, I naught is 0 and for positive sequence I 2 is also 0. There is no, because they will all be carrying positive sequence currents. Therefore, I 1 will be, we can get as VL over 1 minus A square into Z 1, sorry. This is what you will get. If you solve those equations. So, IA will be VA by Z1, IB will be VB by Z1, IC will be VC by Z1. In a positive sequence, voltages are there. VA, VB, VC are the voltages across each of the phases and IA, IB, IC will be the current. So, in positive sequence this will be the relation, Z1 is the impedance. Okay. So, behavior of the machine under positive sequence is analogous to operation of purely forward rotating field. Okay. Now, only thing is I want you to verify this equation. VL will be equal to I1 is VL by 1 by A square, and how do you get that? Okay. Because your VL is, if you take that original this thing, see VM okay, sorry. See equation VM minus VB is VL and VB minus VC is A square VL, okay, agreed. Therefore, with this you substitute what is VA, say what is VA will be V1 plus V2 plus V naught, okay, I1 Z1 etc. Okay. I wish this whole derivation should have been there, okay, in this thing, otherwise one has to work out the whole thing, right. So, I want you to verify this anyway, this equation, right. So, what, because I1 that is I1 Z1 is V1, so V1 will be VL over 1 minus A square. How do you get that? So, please check this. Okay, then you can also see what will be the behavior if it is a delta connected machine. See delta connected machine, let us say this is VL, same ABC. If this is VL, then this will be A square VL, okay, and this will be AVL. You must be very clear about the direction. No, in fact, many books they always wrongly denote V by putting arrows on both sides. Never put like that, it is wrong. Okay. So, VL is like this. So, the currents, if the current is IA, let us say IAL, let us say IBL, let us say ICL, but actual winding currents will be, as a motor will be IAB, IBC, ICA. This is how the current will go, okay. And you should be able to write that IAL, what will be IAL? Will be IAB minus ICA. okay, and IBL, what is IBL will be IBC minus IAB, and ICL will be ICA minus IBC, right. So, you can look at the, so there is relation between phase currents and the line currents, and you are in a positive sequence case, please switch off your mobile. Okay. Now, the if you have IAL will be VL by Z1, IAB is VL by Z1, IBC is equal to A square VL by Z1, and ICA is equal to A VL by Z1. Okay. See, the three there is only a phase relationship between them, okay. IAB, IBC, ICA, okay. And for a, then you have to find out what will be the voltages, what will be the currents in the lines. So, line currents and line voltages are not related by Z1, okay. So, what is important is that you find relation between say VAB, VBC, VCA, these are the line values, and line currents IAL, IBL, ICL, and they are not related Z by just Z1, isn't it? They are interrelated. We only have that IAB is VAB by Z1, that is what we know, and IBC is VBC by Z1, and ICA is VCA by Z1. Okay? Have you understood? So, on a positive sequence, if the voltages are balanced, the currents will be balanced, that is what it will be. But if negative sequence, all these things will Z1 goes to Z2, and your voltages will always be will have a negative sequence, right. So, this is one of the things that we will try to understand. I think you need to work it out. I am just giving you a little thinking, okay, at this point. Now, if you say negative sequence operation, now instead of ABC, phase sequence will be in ACB, and then the rotor is better, but rotor rotation does not change. Okay. So, your rotor is rotating in this way, and your this is the field is rotating opposite to the rotor, field is rotating, because this will be, because your voltages are ACB not ABC. It is not ABC. So, the direction rotating magnetic field, so rotor and field are opposite, okay. And you have the negative sequence equivalent circuit, that will be RS, JXLS, XLR, RR over 2 minus S, and JXM, okay. And this is Z2, negative sequence impedance. So, this is more clear. So, we have V2, Z2, RS, JXLS, this is I2S, I2R, XLR, RR by 2 minus S, this is JXM. So, this is Z2, it is Z1, Z2, what is the difference? One is S, other is 2 minus, because the relative speed of the rotor with reference to the field will be different now. Okay. So, we have Z1 for any given speed, you have Z1 and Z2. If the voltages are balanced, Z2 does not come into picture for positive sequence. If it is voltages are balanced by negative sequence, Z1 does not come to the picture. Okay. So, the negative sequence torque will be T2 will be 3 by omega s I2 R square RR by 2 minus S, okay, the 3 phase, right. So, the torque will be T1 minus T2. What was T1? T1 was 3 by omega s I1 R square RR by S, right. So, you have, I mean, again we have dealt with this, it should not be difficult for you to understand. Okay. So, if there are unbalanced voltages, it will experience both positive and negative sequence torque. So, your shaft will be subjected to both forward torque and backward torque average, and they are also subjected to instantaneous torques. Okay. So, you can imagine the shaft is not getting a continuous torque. So, it will get a sort of twisting torque, and there will also be vibrations. There will be 100 cycles or double frequency thing. So, there is in fact there is also interesting thing. So, the forward field can also interact with the backward fields to produce instantaneous torques, but not the average torque. Okay. So, unbalanced voltages will create this type of problems. Okay. Sorry, I think now this is the negative sequence voltages, sorry, zero sequence. If I apply zero sequence, V naught Z naught, what is zero sequence? You apply same voltage across all the 3 phases. Okay. What will be air gap field? So, air gap field is 0. Ideally there is no air gap field. If you apply pass the same current through each of the windings and windings are in series, so sum of the voltage FA plus FB plus SC is 0. So, whatever flux is only leakage flux. Will be there. So, rotor has no reactions. Okay. So, that is the zero sequence system. So, you have RS only series impedance is there, and you have V naught, Z naught, V naught equal Z naught I naught, because we have done it earlier. Any doubt on this? So, we have Z1, Z2, Z naught for a given 3 phase induction motor. Okay. Therefore, if all the 3 are there, the current in each of the phase will be sum of positive sequence current, negative sequence current and zero sequence current, is not it? If you look at each winding, it will carry all the 3 currents, but fortunately they are all at 50 hertz. Okay. And the voltages will be V naught will be V1 plus V2 plus V naught. Voltage across each phase will be a sum of V1, V2 and V naught vectorially. Okay, they are phasors, right. Then V1 is I1 Z1, V2 is I2 Z2 and V naught is I naught Z naught. Any doubt on this? So, that is how you find out the, sorry, this is VA. Voltage across the reference phase will be V1 plus V2 plus V naught, right. Okay. So, if a 3 phase induction motor subjected to unbalanced voltages, then it will have V1, V2, V naught, it will have I1, I2, I naught. So, each of the voltage can be in return found out like this. Okay. If a 2 phase machine, only we have the 2 windings, say D and Q, you can say V and VB. We said that we have already discussed yesterday in the last lecture. So, VA will be V1 plus V2 and VB will be minus JV1 plus JV2, okay. And we know how to find out V1 will be half of VA plus JVB, V2 will be half of VA minus JVB. So, if it is purely positive sequence, only V1 is present, V2 is 0. If purely negative sequence, V1 is 0, V2 is present, right. Okay. So, this is two phase symmetrical components, right. Now, these are the positive sequence voltages, because we have already seen this, and this is the positive sequence torque, okay. Negative sequence voltages and negative sequence torque. Okay. So, all you have to do is find out V2, Z2, Rs. So, there will be a positive sequence current here and this is negative sequence current here. Okay. This is stator current and rotor current. So, you have no problem in solving them. So, I want you to develop some algorithm. Nowadays with MATLAB you can even develop this. So, you take any induction motor, develop a software, okay, and in which any unbalance can be predicted for the behavior. Okay. So, net result will be T1 minus T2. Any problem? So, you have found out T1, you have found out T2 for an unbalanced condition. Okay. So, now you have to find out the forward torque, the characteristic. This will be forward torque and this will be the backward torque. This is related to due to V1 and this will be due to V2, is not it? And V1 magnitude is not equal to V2 magnitude unless on specific cases, let us say. Is a general case, V1 and V2 have different, may have different magnitudes. So, that way this appears symmetrical, but need not be. So, the net torque will be resultant of these two, T1 and T2. So, this will be T1, this will be T2, this will be T for any per unit speed. Okay. So, an induction machine with unbalanced voltages will experience a resultant torque which is different than a positive sequence torque. Okay. Now, we come to this, when we do this analysis, okay, here first is only due to V1, another due to V2 and this is due to positive flux phi 1, this is due to negative flux phi 2, right. And in this analysis, throughout your phi 1 is constant throughout, unlike what we discussed earlier for a single winding machine. Okay. So, this phi 1 is constant so long as the positive sequence voltage is concerned, and phi 2 is constant so long as negative sequence voltage is concerned at all speeds. Okay. With this analysis, for a 3-phase machine, because we had taken a 3-phase balanced machine, our machine is balanced, voltage is unbalanced, because therefore, this phi 1 is constant and this phi 2 is constant. Any doubt on this basics? So, throughout your flux per pole is same at all the speeds. For positive sequence, certain flux decided by the V1, negative sequence certain flux decided by V2. What is the relation of V1 and phi 1? What is the relation of V1 and phi 1? Huh? Isn't it? You can say V1 and phi 1 related by this. Now, let us look at this. So, what we have so far studied is a normal 3-phase motor with unbalanced voltages, okay, symmetrical 3-phase motor. Now, the single phase operation, say one phase of a 3-phase induction motor is disconnected, okay, and remaining 2 windings are in series. Take a star connected machine, you disconnect one line, okay. This is also one type of single phase operation. So, we have done like that, okay. This will be V, there will be a current I. So, this current here is 0, right. This current, this loop current is 0, is not it, because this is open here. So, what we have done is we have taken a 3-phase machine, disconnect, there is a this is disconnected. Therefore, this IC is 0 and IA plus IB is 0, is not it? Because this is IA, this is IB, this is IC. IC is 0, IA plus IB is 0 and V, so the V equal to VA minus VB. These are the terminal relations. The applied voltage is the difference between these two. Suppose we take this case, so V minus VA plus VB is 0, one relation, IA plus IB is 0, IC is 0, therefore, IA plus IB plus IC is 0, I naught is 0, that means no 0 sequence. I naught 0 and V naught is I naught Z naught, so V naught is 0, no 0 sequence. So, you are only concerned with V1 V2, right. So, in this case there is only V1 and V2, okay. Now, we know that V applied voltage is VA minus VB. What is VA? VA is V1 plus V2, okay, and VB is A square V1 plus A V2, that you know, agreed. Happy with this step? V is this, so you club this V1, so it will be 1 minus A square times V1 plus 1 minus A times V2, okay. So, this will be V in terms of V1 and V2, okay. So, V is 1 minus A square times, what is V1? Is I1 Z1, V1 is I1 Z1 and plus 1 minus A into I2 Z2, okay. I am just making the step by step derivation, and IA plus IB is 0. What is IA plus IB? IA is I1 plus I2, okay. This is IA, and IB is A square I1 plus AI2, is not it? This is again the same relation, okay. IB is A square I1 plus AI2, okay. And from this what do you get? You know, I1, see this is this relation, it will be I1 into 1 plus A square equal to minus of I2 into 1 plus A, is it right? And what is 1 plus A square? 1 plus A square is 0. So, minus A I1 is equal to minus I2 into, okay, right. So, I1 will be equal to minus AI2, is it clear from this? So, I1 is minus AI2, right, or I2 is minus A square I1. Now, you substitute it here, these two things, okay, take it here, okay. So, V equal to 1 minus A square Z1 plus 1 minus A square Z2 into I1, that is because that is what we have done. Substitute for I1, you do not want I1 and I2, you have all, sorry, okay. So, this will be only in terms of, I have removed I2 from there, the earlier equation, because since I1 I2 are interrelated, we have this only. So, V will be equal to 1 minus A square into this I1 is there, this is 1 minus A square Z1 plus what is 1 minus A into minus A square, again we 1 minus A square, right, because this is minus A square and this is A cubed is 1. So, this is same as this. So, common is 1 minus A square into Z1 plus Z2. So, V is equal to 1 minus A square Z1 plus Z2 into I1 okay, or because I is I1 plus I2 which is 1 minus A square into I1. I is IA, okay, because we have taken this is the current input current 1 minus A square into I1. So, 1 minus A square into I1, so this will be I into Z1 plus Z2, that is V, okay. Right. So, I mean it is the same thing. Okay. So, you can represent this sorry I think we can represent it as I equal to V over Z1 plus Z2, is not it? I think we got it somewhere. Sorry. This equation V equal to I into Z1 plus Z2. So, you can always represent, if you have V here and I here, Z1 and Z2, okay. You can write down like that, okay. So, I equal to IA, which is V line over Z1 plus Z2. Whatever you are applying, if the star connected machine, if one phase is disconnected, the voltage current relation will be given by VL by Z1 plus Z2, okay. So, this is the equivalent circuit of 3 phase induction motor with single phase supply. It is a 3 phase number 2 winding series. Okay. And in that case what will be the torque? Torque again will be T1 will be 3 by omega s I1 R square by R by S. So, what you should do is, you know I1, again you go back to the equivalent circuit to find I1 rotor RR by S, and T2 will be 3 by omega s I2 R square RR by 2 minus S, and find the net torque. Is it clear? So, if you have a 3 phase motor, one line disconnected, you analyze like this, so long as you know at each speed what is Z1 Z2. So, at that speed you can calculate the current, okay, that will be supply current. Then from supply current, so what you have to do is, the steps are, you know V, you know Z1, you know Z2, then from this you calculate I, okay, from there you calculate I1, then you calculate I1R, then you calculate T1, and similarly you calculate I2, from there you calculate I2R, then you calculate T2. If you know I1, how do you calculate I1R? Pardon? No. If you know I1, how do you calculate I1 rotor? If this is I1, so this should be I1R, right? You have this circuit, you have to go back to this circuit. So, I would like you to develop this software. So, 3 phase motor under all type of asymmetries, I say, maybe this can be a project for one group, okay. All possible asymmetries you develop a software, okay. If you are given an induction machine parameters, you should be able to predict the performance. But what is the predicted performance means? Current carried, torque developed, okay, and at different speeds, okay. Okay. Now, in this case, one thing we found out was, for this connection I1 equal to I2, right. I1 equal to I2 means what? What does that physically means? I1, magnitude of I1 equal to magnitude of I2. What does it mean? Forward MMF, so that means forward and backward MMFs, rotating components of the stator MMFs are equal. That is what it means. Forward and backward rotating MMFs in a single phase, in a 3 phase induction motor with one line, this is what the situation is. Okay. So, the forward and back rotating components of the flux wave, now, but the I1 Z1, I2 Z2 are not equal in this case, right, except a standstill. See, the I1 and I2 are equal, but V1 is not equal to V2. Therefore, phi 1 is not equal to phi 2. Is it clear? I1 equal to I2 means forward rotor MMF, forward stator MMF is equal to backward stator MMF, because I1 is only stator currents, okay. But the phi 1 is not equal to phi 2, because V1 is not equal to V2 except at standstill, when Z1, because Z1 is not equal to Z2 at all. Any doubt on this? So, our conclusion is, if a 3 phase star connect induction motor one line is disconnected, it will give you purely forward and backward rotating stator MMF, but it will not give you the equal forward rotating, forward and backward rotating air gap fields. So, air gap fields will not be there. So, it is like if you have a magnet, forward magnet will be stronger than the backward magnet except a standstill. Okay, this is a statement. Input impedance of a single phase motor is a combination of positive and negative impedance series. So, that means Z will be equal to Z1 plus Z2 if the two are there. So, this is Z1, this is Z2. Now, no, this is the supposing this is basically hypothesis, again equivalent circuit would reduce to standard equivalent circuit if you say this will be Z1 by 2, this will be Z2 by 2. If you have only one winding, there are two windings in series, this is with one winding, this is one of the assumptions with one winding, but we will do it in a more clearer way a little later in the next lecture. So, sometimes they take this to be single phase motor, we did that single phase motor equivalent circuit as Z1 by 2, Z2 by 2. Okay. Actually, this is ZF by 2, ZB by 2. We did that, no, in some form. Okay. So, the behavior of machine can be understood, and this we have already done. What is the torque due to forward field and backward field due to. So, what will be the torque? Torque is due to this current and this current, I1R, I2R or something. So, we know that single phase motor, this is one way of understanding through symmetrical component. Okay. Now, we will discuss about the zero sequence. Zero sequence, we said all three windings are connected in series or parallel across the single phase supply, right. So, zero sequence may mean, supposing you have a 3 windings, okay, then you can connect all of them in series and pass the same current. Okay. This is zero sequence, A winding, B winding, C winding, they are in series, that means IA equal to IB equal to IC. This is a zero sequence operation. Or you can have another case where you take 3 windings are there, you put them all parallel. Apply the same voltage V. So, that means here VA, VB, VC. So, VA equal to VB equal to VC. Agreed? Either you connect them series, current will be same, parallel voltage will be same. Okay. Now, if you are all same, if they are connected in series, sum of the voltage will be 3 times that voltage IA, right, sum of the voltages. Okay. Then IA is IB, IA is also equal to IC. Now, for parallel connections you have VA, VB, VC both will have the same voltage. Okay. Therefore, in this case I1 is 0, I2 is 0 and I0 is V by Z0. So, in this case I0 will be V by Z0 because your V will have V1 0, V2 0, right. Okay. So, IA is IB equal to IC equal to V by Z0, right, is it okay? Because I1 is, what is IA? I1 plus I2 plus I0 which is V by Z0. So, you have V Z0 IA which is equal to I0. Okay. Right. Now, if the MMF produced has harmonics, because we assumed that with single winding, with each winding MMF produced is purely sinusoidal, that is what we assume. Okay. But if they have harmonics, that means you have a, supposing you have a coil A dash, okay. Ideally you would have expected it purely it should be, this is the MMF distribution, is not it, this is ideal, okay. But it may have, in actual practice what it will have. So, it may have some, maybe it will have something, okay, some combinations may be there, this is actual. So, there will be also various harmonics, let us say. So, there may be third harmonic, so there may be fifth harmonic, okay, third, fifth, right. So, it will have first harmonic, third harmonic, fifth harmonic, seventh harmonic. Why not second, fourth? Huh? Huh? Because of symmetry of the windings, because their all axis is here only. So, if you take this as the axis, it will all be cos theta, cos 3 theta, cos 5 theta. If you take this as axis, it will be sin theta, sin 3 theta, sin 5 theta. Is it okay? So, you can represent the MMF as its in terms of the current into some constant into cos n theta for A phase, B phase current IB into some constant cos n theta minus 120 and this will be cos n theta plus 120. This is the total MMF produced if they are, it is general expression. This is for nth harmonic number, it can be 1 to infinity depending upon the number of harmonic. Of course, we invariably after 3, 5th, 7th etc. they become, design is such that they become weaker, does not matter. Then if this is one, but IA, IB, IC are same, when IA, IB, IC are same, then if the 3 currents are same, then this term will be same, okay. Then you will have cos n theta minus 120 etc., right. And so, number of turns in series per phase and winding factor for nth harmonic. What is Kn is the winding factor of nth harmonic, that will not be same as for fundamental, okay. So, if the 3 currents are same, you will have the MMF as, supposing current is I cos omega t, current is sinusoidal in the windings. So, it will have a n equal to 1 to infinity k n cos theta n cos n 120. So, that will say n phase into I cos omega t. If you take up these ones, you will notice if it is fundamental, 5th, 7th etc. will vanish, only third harmonic will be present. only triplen harmonics. Okay. So, I want you to check this, will you? You may confuse yourself, because if A winding has a set of MMF sitting there, B winding will be same after 120 degrees for fundamental, right. So, you will see whether many of these things will at any, you will see that all the fundamentals will vanish, all the fifth harmonics will vanish, all the seventh harmonic will vanish, only third, ninth, like that it will be there. Huh? Yeah, third, ninth I am telling you, I did not say sixth. Okay. Where? K3, K6. Oh yeah, this yeah, this will not be there. It should be K9. Okay. And if you neglect other things, that means you are concerned there will be a third harmonic, which will vary like this, cos omega t cos 3 theta. Winding currents are fundamental, but it is like a triplen poles. If the fundamental has 2 poles, the third harmonic will have 6 poles. Okay. So, 6 poles means the electrical angle will be 3 times that. Agreed. So, you have a, is it clear now? If you have 0 sequence operation, if there is a, so air gap will have 3 times the poles of the fundamental. Okay. So, now, so the resultant field is similar to a single phase machine having 3 times the number of poles. The equivalent circuit is similar to that of single phase motor, except that the values of slip and Xm will now be referred to third harmonic field. So, you are trying to write an equivalent circuit for third harmonic now. Okay. So, this will be a typical circuit that you will have, apply a single phase winding. Okay. This will be RS, this will be JXLS. Okay. Now, I have put 2 switches S1 and S2. Now, this is a switch S1, this is a switch S2. So, which circuit will be operative at what conditions? This is, after all, we have got a Xm by 2, Xm by 2 as the usual this thing. This is X2 by 2, so XLR by 2, I will say XLR, because let us be consistent, and this will be RR. Now, this is RR by 2 into 3S minus 2. What is this? This is the for the fundamental forward rotating field with triplen poles, where S is for fundamental. So, if S is 0.1, then it will be 3 into 2 into 3S minus 2, okay, and this will be 2 into 4 minus 3S. These are the slips, 3S minus 2, this will be 4 minus 3S. Is it clear? That means you have to find out this, you have to check this. Now, your synchronous speed is 1/3 of the original. So, what it means is, see, what it means is, this is the normal characteristics, fundamental. If this is S equal to, supposing this is the S here for fundamental. Now, but for the third harmonic, this will be Ns by 3, isn't it? So, this point will have a different number. For fundamental it is S, for this what will be the slip? So, the slip here will be Ns by 3 minus N over Ns by 3, where N is the speed. Okay. So, compared to the fundamental, that is what it will be. Okay. So, the equivalent circuit, okay, have you understood? Speed is same, your slip is different for different harmonics fields. Fundamental slip is S, for triple harmonic it will be something else, because your synchronous speed has been different. Synchronous speed is 1/3 of the original synchronous speed. Okay. So, the equivalent circuit will have 2 switches, S1, S2. If the rotor is wound for fundamental number of poles, If the rotor is one of fundamental number as a slip ring machine, unlike in a squirrel cage, then what will happen? It will not react with third harmonic field at all. So, S1 is open. So, S1, this switch is open, okay, if it is a slip ring machine, because it does not react to other than the fundamental poles, right. Then what other thing? Now, if the stator has 120 degree spread, that means K3 is 0. If you make a 120 degree spread by design, you can prove that third harmonic is absent. If the third harmonic is absent, then when there is no third harmonic, okay, then this will be taken care of by closing S2. So, if third harmonic is not there, you close S2. So, this is general single phase motor equivalent circuit. This is for slip ring machine, the rotor is open, and for a squirrel cage machine it will be you close the switch if third harmonic is not there and open the switch if the third harmonic is there. Okay. So, these are the broad this thing. So, zero sequence operation of a machine cannot be used for normal single phase operation unless operation at 1/3 the synchronous speed, right. So, that is what we will. So, this is the typical torque speed characteristic with zero sequence operation. This will be the torque speed characteristics, because this is the 1/3 the synchronous speed, is not it, your 1/3 the synchronous speed. So, even if a normal 3 phase motor is there, a squirrel cage one, if third harmonic is present, even under a single phase it will give you the third harmonic torque. So, you can see the T3. Is it okay? Okay, we will close it here.